Hello, everyone.
Hello, good evening.
Hi.
Hello.
Hey, Jason. All right. So good to see you guys. I hope you guys had a great week. Yeah. Wow. Something big happened over the weekend, right? So we are witness this historic, unfolding in real time. So hopefully, this war or operation, let's hope will end very soon because it had a lot of impact, right? So let's see, let's hope it will end soon. And so before we get started, any question regarding what we talked about so far, regarding the material, the method, the models we talked about so far? No? All right. Then if not, let's continue. Yeah, we got a lot of stuff to talk about today. All right. So so let's continue. We introduce this so-called ALMA model, which is very convenient. All right. So ALMA, this model is like we call it cyclical, and remember we talked about this seasonality things before. So we actually can combine them together. So let me give you an example here. So if you look at a time series like housing starts, all right, meaning like a housing supply by monthly data, and you can see here, all right. So sometimes you might encounter this kind of series, right? So there's up and down. This is great recession. Financial crisis. After housing bubble. This is housing bubble. But beyond this kind of business cycle, we also can see this kind of periodical up and down, and we know that is about seasonality because it had this kind of peak and down trot every 12 months. So it's obvious this is a seasonality, and based on our understanding, it makes sense. This is seasonality. All right. So right now, let's look at this. Okay. This is an autocorrelation function we spent some time to talk about last week, and it makes sense, right? This is the autocorrelation part, which is sensing foundation of the signal we want to see, we want to capture. And then here, this is another interesting one. Right? It peaked at 12 months. This is monthly data. So we know, every 12 months, there's a stronger relationship from this month to 12 months ago. So we know that is seasonality. All right. So based on that, we can kind of use that to kind of predict this signal and then use that to predict the future. So here we can say kind of try to speculate different kind of model. So this is like a ARMA 2-3. So you can make it like ARMA 2-2-2-1-1-2. But here 1-2-3 is like all right, it should be good. All right. So that's that. Okay. Okay. So that's that. And then here we can add this seasonality. All right. So right now this is the ARIMA function in R, and I noticed that in Python, let different library to do this ARIMA model, and different library had different kind of setting format. So sometimes some is more complicated, some is simpler, and when you compare the result, they might have some kind of a little bit small digit difference. But by and large, they should look very similar because they are following the same kind of model structure. So don't worry that too much. It's up to you what kind of format, the model library you are used to. You can use that. But here in R, I like to use this is just ARIMA, very straightforward. All right. So here seasonality here, this a little bit different setting, you know, one. Let's see how it works. Alright. And here, so this is a cyclical part, ARMA 2.3, right? Seasonality here I had is 12 because I know based on the observation of the autocorrelation function. So this pattern should repeat every 12 months. So I had is 12 in AR term. So this is MA term, all right? So let's see that. And here this is MA term, and this is both AR and MA, all right? And this is just a seasonality, but we just gonna ignore the cyclical part, AR part, all right? And this is another format, you know, it's like a ARMA, and seasonality use this kind of weird way. Anyway, more complicated way. See how it works. Okay, all right. So right now, let's look at this so-called accuracy. Right? So, where is the result? Hey, where is it? I cannot see the result. Okay, so what's going on here? Oh yeah, here you go. Okay. All right. So last time I said usually I look at there are a bunch of different measurement in terms of forecast error. I usually like to use this root mean square error. So look at that. 15, 14, 11, 12, 10, 10, 10. So it looks like this is way off, right? So this means if this strong seasonality series and you ignore that, that is not good. And then this seasonality setting is wrong, so it's not good because it's every 12 months, not every 1 month. So this is no good. So model 7C become better, right? And this one is a little bit old. Anyway, things like the final three are pretty good. So final, this is 7E, F, and G. So that means for this seasonality, if you can model 12, 12 for both AR and MA turn, that is the best. All right. So this one, and even this one is good. So it turned out to be this is not really that important, yeah. So it's kind of funny, but turned out to be this one is the best. Okay, so if you want to model it, you can use this kind of way. Okay, and did we talk about this auto ARIMA yet? Did we have talk about that auto? Oh yeah, I think we talked about this, right?
I don't recall.
Oh, okay. All right. So it's okay. Let's go back there. Yeah. So auto ARIMA is essentially like a shortcut. If you feel like this is a little bit tedious, you know, yeah, it's kind of, I don't have time for that. You can use auto ARIMA. So basically, it will find the best. Okay. So let me go back to here. Let me go to. Where is it? Housing. Yeah, here. Okay, just kind of review. This is housing price return. All right. So let's go here. All right. This is the last time we had that different kind of model. Just like what we talk about here. Without seasonality, it's simpler, right? So here we kind of use this so-called auto ARIMA. All right. So basically, it just choose this ARIMA model for you. It means with this series, the best model is ARMA 1-2 model, and then you can see the coefficient AR1, MA1, MA2, and this is intercept term, and give you some kind of a low likelihood AIC, BIC, this kind of stuff. So basically, yeah, just telling you ARMA 1-2. But sometimes the result will be a little bit different from this one. You know, this one, remember last time we choose, I think the best one is actually ARMA 22. Yeah. You say, what's going on? Why this is ARMA 22 and this is ARMA 12? So I don't see there will be too much difference. But if you want to be sure, you can try this way, you know, kind of, you know, more I think more prudent way. Yeah, this one is a kind of shortcut. You know, you don't want to spend too much time on that. You know, just kind of a little bit lazy. You know, just ask the model to find out the best for you. They probably they are using different kind of criteria to decide what kind of order of the model being the best. So yeah, so. Yeah, I don't think they present a material difference, right? So AutoArima, yeah, and so here this is so-called home price return data, and this one is a home price label data. So without doing this, what is that? Yeah, remember? Yeah, we do this. We convert this home price to this log difference return data. So without confirming that, without doing that, you can actually. So this is very handy. So right now we have this time series with obvious trend, and we say that is actually non-stationarity data, right? If you encounter that, we can just the same thing. You can just run it. Alright, so did you see that? The same series, but with different kind of format. One is return series, one is label series. You see, it suggests you ARIMA 022. So you say, what does that mean 2 here? I'm gonna explain in more detail. Just keep that in mind. So here, these 2 means we are gonna take the twice of the difference of this data set to make it stationary. And then with that, we run this MA2 model. So that is the way we explain it. I will talk about this more. All right, and this is, yeah, just the same thing. We use that to forecast. Yeah, ARIMA 12 model. Yeah, so home price return will be positive and a little bit slower. Yeah. Okay, so let's that. Okay, here. So let's go back to this AutoArima for this series with seasonality. So here I think they had this kind of setting. You can just say seasonality is true, and let's look at what happened. Yeah, turned out to be this kind of model, you know, for whatever reason, it's not that good. You know, it's kind of yeah, not good. So I would not suggest that. You know. So AutoArima, yeah. So what that means, you probably need to go back to use this kind of you know, tedious way. You know, you need to have this setting. Don't rely on AutoArima. So for Python, for that, again, as I said, they had different kind of library, and each library they had different way. So you kind of probably need to try to get yourself familiar with all those kind of different setting. I think in my website, course website, I had this kind of example you can use. You can check it out. I think they are a little bit more complicated, you know, in Python. Maybe right now they are some kind of new library which will be easier, like this kind of AutoArima function. So you can kind of get yourself familiar with all kinds of different way to do that. But the concept is the same. And again, as I said, sometimes their calculation will result a little bit slightly different kind of suggestion. So it doesn't matter that much. I notice it's okay. You know, usually they kind of present similar kind of trajectory or pattern or dynamics of the forecast. Okay. So, all right. So go back here. All right. So this is the model, right? We find this is the best model. So this is so-called the model procedure. And right now, remember, if you still remember, this is what GGTS display basically is checking the autocorrelation function of the model procedure. All right. So just keep that in mind. So let's take a look. So this is model residual. So what's the model residual? After we model ARMA 2-3 and with seasonality for this housing star series, this is the model residual. All right. So you say, what do you think? Looks like remember in the very beginning of this class, there's a fundamental idea of this model. So we have the data is comprised of a signal and noise, right? So we use the model to kind of extract all kinds of signal in the data, and the rest is the noise. So the model residual, the ideal model residual should look like a noise, right? Random noise. Does this look like random noise? Kind of like, right? Maybe here is a little bit cluster, you know. So, but anyway, let's look at the part of the signal is autocorrelation. So when we run the autocorrelation with the model's residual, and what does this say? There's no autocorrelation, right? Because they are all within this a critical level, threshold level. So no residual. So that is good. So that means, all right, you probably are doing a pretty good job extract this autocorrelation in the series. Yeah. Okay, so this is good. And this is another way, I think. Yeah, and check the, you know, another thing is like you want to make sure your so this model's residual. So in other words, you can say the model residual is like a forecast error, right? You use a model to predict, and then the model residual is the noise, right? So you want to make sure the forecast error should be centered at 0. Anyone know why? Well, we kind of use a common sense to explain. You know why I say that? Because this is like a model residuals distribution, right? It looks like a normal distribution, but why it should be centered at 0? What if it's not 0? It's a 1, 2, 3. What does that mean? Anyone know?
Prediction would be biased.
Exactly. Yeah. So the model, if you had a model residual or forecast error like not being to 1, not being to 0, it means that you are constantly making some kind of a forecast error, either is positive or negative. You are constantly overestimate something compared to the actual value, or underestimate. So that is not good. So this is another necessary condition, right? So not only no autocorrelation, but your model residual forecast error should always center at 0. Yeah. Okay, but usually when you use this ARIMA model, usually you should be fine. Yeah. Okay. Right. So what's this? And then we can use this forecast. All right. So did you see that? So beautiful, right? So it kind of captures that seasonality pattern, and also some kind of a cyclical pattern, you know, going up a little bit. Yeah. So that's that. And what is this? 7E, and F. What's 7F? Similar. E and F turn out to be similar. Okay, all right, and this is some kind of simulation. Oh, all right, all right. Any question? All right. If not, let's get back here. So this is what we just talked about. All right. So right now, let's revisit this concept, stationarity. As I said last time, it's a very important concept. Usually, if you are not in this field, you don't know this term, but right now you know, right? So, as I said last week, stationarity is a necessary condition for forecasting, right? So we need to make sure that the series we are analyzing is a stationary series. But right now, we might say, okay, then what if we are encountering this non-stationary series? Does that mean we should not touch it? Actually, no. We should try to figure out a way to transform the series to a stationary series and then analyze it. And one of the way, like AutoArima, they will do that for you. So right now, let's kind of break it down. What exactly the situation you should do? All right. So the first one is this is so-called very common things. We can do is like a log transformation. We take log of the series, or more general way is the Cassbox transformation. It's a general form of this transformation. So if you had some kind of series, remember we had this retail sales up and down, and then over time it just become the range just become bigger and bigger, right? So usually that is because we are looking at a long-term time series. We had this inflation, so it just get larger and larger. So something like that, you take log, it will be an easy fix. All right. So with the trend data, usually trend data is non-stationary data. So what will happen? You should do a two-way. First one, there's a trend, you detrend it. All right. And here, did you see this term? Deterministic trend for deterministic trend. But most of the time, the trend data, it is this kind of trend called stochastic trend. So in that case, you should not detrend. All right, you should say take the first difference or take the growth rate, log difference, compound growth rate. So that's the easiest way to do that. And most of the time, if you use the AutoArima, they will just kind of go to this default setting, treat the trend like a stochastic trend. So right now you might say, what's the difference between deterministic trend and stochastic trend? Yeah. So this is a very important concept in time series, and a lot of people don't know. So here, very easy definition. So deterministic trend is you are pretty sure where the trend will end up. Okay, and a good example is that linear trend model we talk about. Remember we talked about this trend one, model 1, model 2, linear trend, quadratic trend, log linear trend, all those kind of things, right? So basically, that is under the assumption that trend is the deterministic trend. So you can use that kind of very straightforward way to model that. However, a lot of time, the trend series we saw, it actually is stochastic trend. So what is stochastic trend? Anyone know? Hey, anyone heard of this term, stochastic trend? So stochastic means actually you don't know where it will end up. So that is kind of very funny and scary, right? So okay, what are we talking? What is William talking about? So we are talking about this model, and then in one thing is like okay, we can model it, but the other one is like actually you are not quite sure how you are gonna model it. That is exactly what I'm talking about. So that is the stochastic trend. All right. So let me kind of go over this kind of concept. So stochastic trend, actually there are several different names that represent similar things. Sometimes we had a term called random walk. Have you heard of the term random walk before? Actually, there's a book about stock market written several decades ago called random walk down the street. It's talking about how you should. It's a great book, about a stock market investment. So it's kind of talking about this kind of concept. Right. So, so just imagine that you probably have seen this kind of TV, like a police cam, and like they kind of pull over some kind of suspicious drunk driver, So basically, they can use this very simple way. Hey, have you seen something like that, right? They just say, hey, usually drunk drivers say, I'm not drinking, I'm sober totally, right? So they just ask the driver, you walk a straight line. So if you are fully sober, of course, nobody had no problem just walk straight line, right? But usually a very drunk person cannot walk a straight line. So it kind of like a, here and there moving. So basically what happens is that stochastic trend or random walk is just like a drunk, very drunk person walking down the street. So you don't know where it will end up because he doesn't know. He cannot control himself. He's not sober. So he can end up to the right or to the left or to some kind of place in the ditch, right? So that's all possible because he's not really controlling himself, right? So that's the kind of concept of random walk, all right? All right. So here, so let's kind of revisit. So we talk about this deterministic trend and stationary series. So they are the same thing, because it's deterministic. When you detrend it, you figure out a linear trend or quadratic linear trend whatsoever, and then the rest, the detrend series becomes stationary series, right? So when you see something like this, actually there's a very subtle underlying assumption behind it, all right? So here, this is it. The shock hitting the series is temporary. Okay, it's temporary. Or sometimes I will say small scale, non-material, temporary, all right, transitory, whatsoever. Right? So because of that shock is temporary, so it hit the series and it got deviate a little bit. Because the shock will remove itself in no time, so the series will go back to the trend. Okay? So that is under the definition of stationary, right? Deterministic trend. So any deviation will come back to the trend. Sometimes we have this term called mean reversion. Have you heard of the term? So usually that means the series, the shock is temporary. Yeah. And when we run this autocorrelation function, you are going to see that autocorrelation function dying out exponentially. Yeah. And then there's a term, statistical term called I0 series. So I0 series is this beta 1. The coefficient should less than 1. And remember the example I gave you last time? I used the height, the parents' height and children's height as an example, right? So that beta 1 it is exactly like that. If it's bigger than 1, that's not fully explosive. And if it's equal to 1, then the whole series become stochastic trend. All right. And if it's less than 1, then we say, okay, that is a stationary series. Right? So that's the concept I0 process. Okay, and this typical AR1 process. All right. So stochastic trend. The underlying implication is the shock hitting the series is a permanent shock. Okay. And because the shock is a permanent shock, or we can say in other different ways, a large scale shock. Right? Any deviation will not come back to the trend. Okay. So So sometimes, let me give you an example. So you say, I don't quite understand what this means. So every day we live in this kind of very busy world. A lot of things could happen, right? So for example, you might get some kind of good news or bad news from your work, from your relationship, right? So say something like that. And sometimes good, you mean you will become very happy, right? And bad news, bad thing happen to you. You know somebody kind of scream at you at work. You know this could happen. You know sometimes it happened to me, right? Your colleagues, co-worker disagree with you, and then kind of had a big fight with you, and you feel very, very bad, right? But that kind of bad feeling usually will kind of drive down your mood, you know, happiness, you know, for a short period of while, right? But eventually it could go back. So that is like this shock. The good news, bad news is your life. And then in few days, maybe in few weeks, you kind of back to normal. So you forget what happened, that good news or bad news, right? So that is the idea of stationary. But sometimes some kind of shock, whether it's good or bad, is very severe, large scale. So when it hit you, it changes your life forever, whether it's a good one or bad one, right? So that is the concept of stochastic trend, right? So that is what I'm talking about. So that deviation will be permanent. So you are not gonna go back to the original trajectory of your say life or mentality, something like that. So that is a stochastic trend. Right. So in that case, when we run this autocorrelation function, you're gonna see autocorrelation hardly dying out. Right. So sometimes we call it I1 process. So the beta 1 is 1. So basically you say, oh, it's kind of weird. So this is 1. What does that mean? It means actually the yt, and this is yt minus 1, will be purely dominant by this shock. So when shock happen, you know, you kind of had totally unpredictable things here. Yeah. All right. So right now, so basically just kind of summarize the difference between these. This one, stationary series deterministic, is easier to model and predict. And this one basically is saying that no way to predict it. Okay? And I'm gonna tell you, if there's no way to predict it, how are we gonna make it into the model? I'm gonna show you today. All right. So here, let me give you the kind of visualization to help you understand the importance of this concept. All right. So here, remember we talked about the series is like just keep in mind that there's a trend and cycle, right? And right now we are talking about actually in terms of trend, there's a fundamental two different kind of trend: deterministic trend, stochastic trend, right? So right now, if you look at this, if you observe any kind of this time series, and you look like this, you know, up and down, right? So our idea in time series, if you can kind of understand the underlying trend, and you're gonna see how it will help you, right? For example, if you can kind of calculate, okay, we figure out this up and down actually is fluctuate around this dash linear trend, deterministic trend. So how is it gonna help you? It's gonna help you to forecast, because what? Because by definition, if this series follow this deterministic trend, it means what? It's gonna go back here, right? And if you further deviate from the trend, this mean reverting process will be even stronger, right? So that is concept, mean reverting process. And you say, then why? Why there has a kind of deviation? Because all kinds of transitory shock, right? Okay. Okay, so this is deterministic trend. How about stochastic trend? Stochastic trend is, by nature, the shock hitting the series usually is a permanent shock, large scale shock. it hit you, you had a new trend. Okay, so before it could be like that, but something happened, and then you follow this new trend. So what that means is there's no original deterministic trend to go back to. So if you are expecting, oh, I should go back, so they should go up, but turn out to be no, it just stay there. So it make it very difficult to kind of make a short-term or medium-term or even long-term prediction. Yeah. So it's very important to kind of make a distinguish of deterministic trend and stochastic trend. All right. Any question? All right. So this is kind of like a economics, finance kind of concept, time series concept. But in fact, in physics, that has similar kind of concept. If you, I don't know anyone's physics major, so long time ago, a century ago, we had this debate. These two famous Nobel Prize winner in physics. They had different kind of a view about the universe. Yeah. Imran, you had question?
Yes, Professor.
Yes.
So there are terms that I'm hearing: detrending and differencing. Are they different? Like the differencing is also like detrending the trend, right? Or is it different? Is detrending and differencing different?
The trend and the difference. Is that right?
Yes.
Is that what you are talking about?
Yes.
Oh no, they are different. All right. The trend is for stochastic, for deterministic trend. So that means looking at this time series, you observe the trend is pretty linear to some degree. You're pretty sure that pattern will continue. So you observe that in the history, it will continue the same way into the future. So in other words, that signal will continue. So that is deterministic trend. So if that is things, then you just kind of figure out the trend and then you detrend it.
So I guess my question is that the bullet point says detrend for data. So how do we detrend it?
Oh,
Yeah.
Okay, sorry. Yeah, I forgot to mention. Actually, it should be here, right? So maybe this is not quite easy to understand. Maybe next time I should add this. So this is U.S. The blue line is the U.S. GDP. So you see up and down. So if you can figure out like a trend, all right. So this is like a red line. I don't know. This red line seems not quite good. That is the trend. So what happens is that you figure out, you make a prediction of this red line, the trend line, and then you calculate the difference between the original series and this red line. So that process is the trend. So basically, it's like you figure out a trend, and then you move that trend to horizontal. So that is the trend series.
Okay. So basically it's like, so this red line is the predicted trend.
Mm-hmm.
So basically you mean the error is detrending?
That's right. Yes, that is.
Error would be detrending. Okay.
Yes, that's it. Very straightforward. And linear trend, like whatever, there's some kind of like a different filter. They do this kind of detrend things. Yeah, there are all kinds of. Maybe one day you're gonna figure out another way to do this kind of trend. But whatsoever, whatever the complication you had, remember we had this whole trend things we talked about before. Yeah, you can do that and then make a detrend series. You make a prediction and you calculate the difference of the original series and that trend predict line. So that's the trend. But just keep in mind, when you do that, it means that trend signal will continue into the future. But today we just learned actually there's a totally different kind of new world. Is the trend you saw that's a trend, but actually it's a stochastic trend, and that stochastic trend makes things very difficult to capture. All right. So
thank you.
Yeah.
Thank you for that question. So now I finally understand.
Oh yeah, you understand? Okay, yeah. So yeah, I should make it clear about how this trend things is going on. Yeah. Okay. So this Einstein and I think Bohr, they had different view about universe. So can you guess? Which one is following deterministic trend? Which one is stochastic trend? So Mr. Bohr say, don't tell God what he can or he cannot do. All right. So Einstein said God does not play dice with the universe.
Einstein is deterministic.
That's right. Yeah. He figured out God, the creator, had a kind of deterministic kind of view. What the universe will go. Eventually, and then Bohr said, don't you don't know what God. So it's kind of interesting, right? So then the question you might say, okay, so how do we know how are you gonna see this the universe? Actually, let's not go that far. Physics, quantum. Wow, that is too complicated, right? Let me ask you guys this question, right? Can you tell? So right now, a lot of things is going on, right? We had AI, we had Iran war, a lot of uncertainty. But that uncertainty could be noise, could be some kind of short-term kind of a cycle, right? So let's just say, if I ask you this question, like in 100 years, what do you think the world will be? Okay? Maybe not perfect prediction, maybe just some kind of big direction. The world will be in a better place or worse place in terms of everything, in terms of economy, society, whatsoever, in 100 years. Anyone have any idea? The world will be either in a very good place or very bad place, or you don't know. Which one? Anyone has some kind of opinion? Maybe this is philosophy, but let's just kind of, anyone have very strong opinion in 100 years what the world will be with this technology, with whatever geopolitical change? Anyone?
I would prefer to be positive and believe that we will be in a better place in 100 years from now. Yes.
Okay, so Spinoza, your view actually is deterministic view. It's good. Yeah, you're pretty sure you will go out at a better place. That's good. That's very optimistic. I like it. Yeah. Anyone had different view? Eric, you had different view?
I'm with the stochastic view.
Okay, so you don't know, right?
I don't know.
No. So yeah, you don't know. It means what? Maybe human decision making over the next 100 years will change it. So Spinoza means whatever we make a good decision or bad decision, eventually we are gonna become better. So that's the deterministic view, and the stochastic view is we don't know. So I cannot tell you which one is correct or is incorrect, because that is pretty big things. But I don't think we need to agree on that, But the concept, I think we should know, what does that mean in terms of figure out the signal and making a forecast, right? But and is that clear, anyone? So these two fundamental things are very different concepts: deterministic, stochastic. Okay, all right. All right. So right now, let's talk about, okay, so let's just say this series is a non-stationary series. And actually, we had this so-called unit root test. You can see a lot of this kind of package doing this unit root test. Actually, when I was in graduate school, we learned this unit root test. There's like hundreds of different kind of unit root tests, And you say, what's that? It's testing that whether the beta, it's kind of pretty funny. It's testing this beta is being 1 or still less than 1. That's it. And if 1, it means it's stochastic trend. And if it's less than 1, it's stationary series. So
Okay.
so we had this kind of unit root test. In fact, you guys probably don't know. Remember, I show you this real GDP, right? In fact, I don't think we economists still had a very decisive conclusion. Even the U.S. GDP is a deterministic trend or stochastic trend. Can you believe it? Even right now, we still can, every once in a while, some economists say this is deterministic trend. Some economists say this is stochastic trend. Actually, it's kind of funny, yeah. So even like a simple series like GDP, we still cannot figure out. But there are something I was gonna show you. Actually, it's very straightforward. We know for sure that is a stochastic trend, or not. Okay. All right. So if this is stochastic trend, random walk I1 process, so what we need to do is do this so-called difference. So basically, it's just a take difference. So the current period value minus previous period value. And if sometimes we do the log difference, actually it's kind of growth rate, compound growth rate, right? So when we do this once and it becomes stationary, so that is the so-called I1 process. But if sometimes I1 process is not enough, we do it twice. So that's I2 process. Like some kind of price, I would say probably like the Bitcoin, price, commodity price, something like that. It might take twice of we call it integration. So this is so-called integration. So become a series. All right. So right now let's look at this. If we use this auto or Riemann function to run a series, and it looks like there's a trend, and then result is that okay, we suggest the best way to kind of run this series is Riemann 213. So 2 is AR2 order, 3 is MA3 order, and the 1 is what? Is this series is having a stochastic trend. So even like we look at like let's upward sloping trend, downward sloping trend, but actually it's a stochastic trend. It means what? The trend you look at actually is no way you can predict that. That's a definition. And then you take the first difference to remove that trend, to turn that series to a relatively stationary series. And with that stationary series, you will capture this cyclical part, AMA 2-3. And this AMA 2-3 is something having a repeated pattern you can use to predict. But this part is something you cannot predict, so you should give up. So that is the idea of Riemann 213. Okay, so yeah, later we're gonna see some example, and you will have a better understanding. All right. And a lot of time, sometimes we just kind of directly using the growth rate series to model it. When you see that, actually it means there's underlying things. We kind of use growth rate as a stationary series without kind of encounter some kind of issue, non-stationary issue. Yeah, in Ray? Yeah, you have a question?
Yes. So if we take the difference with D is equal to 1, I'm trying to understand what is D is equal to 2. Is it applied on delta YT, or is it like YT minus YT minus 2? Is it a two-step difference, or is it a difference taken 2 times? Like first time it is YT minus 1, so we get the delta YT, and the second differencing is applied on delta YT. Is it like that, or is it YT minus YT minus 2 two-step difference?
Oh, okay. Yeah, good. All right. So if you say this D is 2, right? What's going on? Sorry. So the answer is you are calculating because this is d equal 1, right? So you are gonna calculate another run. So you are gonna calculate delta yt minus delta yt minus 1. So you are gonna have 2 delta. Yeah. So
Okay.
that is d equal to.
So another question on the same thing. So we are taking the difference with one time step.
Yes.
What, and if it doesn't make it stationary, can we try with a delta of 2 time steps and see if that can make it stationary? Instead of like yt minus 1, if we do yt minus 2.
Oh, okay. That is interesting. As far as I know, I never seen something like that. I never see something like that. What usually happen is in practice we had this so-called. You guys probably know when we do this growth rate, we either do like this, right? You just compare to the previous period, and the other one is very common in practice. So, for example, have you heard about year-over-year growth rate? So that is something like what you are suggesting, but usually that year-over-year is trying to overcome this seasonality. Okay.
Exactly. So say for example, if we have quarterly data and we try to make it stationary by taking a difference of 4 steps, yt minus 4, because in 1 year we have 4 quarters.
Yeah.
And that makes
okay.
it stationary.
Yeah. So that's fine. But yeah, we're gonna see something like that. There will be some kind of problem. I'm gonna get to that. Yeah, it's possible. In fact, let me see if I can show you.
It sounds like a seasonal differences.
That's right. It's a seasonal difference. So let's just say GDP, right? GDP.
Yeah, the objective is to get the seasonal patterns, but it's not the standard differencing of step 1. Rather, it is differencing of step 4.
Yeah. That you can do. Yeah. So let me show you this. For example, this is real GDP US, right? You can add it. Right.
Probably more properly say it's a differencing of lag for.
Yes, lag for.
Yes.
Yeah.
The differencing is more akin to taking a derivative, and taking a second derivative if you had the first difference compared to the second difference. And I think the only way it's different from a true derivative is we're only taking the numerator of the derivative. So in other words, your change over time, your change in y over time, you're just looking at your change of y. You're not looking at the change in time. That's how it's different from a derivative.
Oh, okay. Yeah, Eric, you are talking. In fact, we might be able to talk about that a little bit, at the end. So here we are this is so-called discrete, so it means actually you can really easily compute. So what you are talking about is that kind of derivative calculus concept actually more like a continuous time series. In fact, they are similar concept. It's just they are calculating this so-called time difference in a much smaller interval. So is that what you are trying to say?
Yeah, I'm making an analogy between derivatives, between a first and second derivative, and I'm making the analogy towards a first and second difference.
Yes, that's right. Yeah, that's right. But first derivative. Yeah, I don't know if they emphasize stationarity a lot. Yeah, maybe so. But yeah, you're right. They are very similar. Yeah, it's just one is discrete time series, one is a continuous time series, but the logic is very similar. Yeah.
Yeah.
Okay. Here.
So basically, what I wanted to understand is that if we take differencing instead of like one lag, if we take differencing of multiple lags, would that be conceptually correct or not?
Say again. If we take difference in
instead of one time step, we take difference of like 4 time steps or 3 time steps, would that be conceptually incorrect or would that be conceptually okay?
Oh, okay. Let me kind of give you an example here. All right. So very good question. So this is a series, very important series, United States real GDP, right? Represent our economy. So you can see here. So it looks like there's a trend, right? Upward sloping trend. And then here, and then you can do a lot of kind of so-called transformation. Like one thing is like you take log, it become like that, right? Okay. So let's go back here. You can see there's a default setting. So here, there's a change, and there's a percentage change. Percentage change basically is like a log difference. So the change is like a difference. So let's look at the percentage change. So this is the series. So this is like a real GDP from one quarter to the next quarter's growth rate. All right. So that's like a YT minus YT minus 1. So this is one way. And right now, did you see that? Did you see that? There's a percentage change from a year ago, from 4 quarters ago. So that is a log difference, a YT minus 4. So let's see. Right. So you see, you got different kind of result. So in economic year-over-year growth rate. So we are looking at the same time series, but it gives you different information. So this one, percentage change is just telling you, you know, how the economy change from one quarter to the next. And you might say, okay, so this kind of, it could be a lot of noises, you know, involved, you know, but we want to see something a little bit long term, and then we can try to overcome some kind of, at the same time, some kind of seasonality kind of problem. Yeah, we had year-over-year growth rate. So later, I will give you another example to kind of show the difference. But the short answer to your question is that it depends. You can use both. It depends on how you're gonna explain this kind of things. You know, in economics, we had this very straightforward way to say year-over-year growth rate, or you know, whatever periodical growth rate. So
Thank you for showing this, because this trend on the screen, it's looking much better than the percent change, because that is looking like just noise. So yeah, thank you.
yeah, so usually it's like that. For example, you guys probably I'm not sure if you know it, like it's like a famous CPI. Yeah, this is CPI series. You know, basically non-stationary, like it's kind of very good trend, right? So usually, if we do this so-called percentage change, yeah, did you see that? That means our price level from 1 month to the next, so it's up and down. But if we do the percentage change from a year ago, so just look at this. Wow, did you see that? Much smoother. Yeah, much smoother. So kind of usually this is so-called year-over-year CPI change. Actually, that is the inflation we usually heard, like 2.6, 2.7, those kind of things is from here, year-over-year. So it's YT minus YT 12 legs, so 12 months ago. But there will be some kind of problem here, so we're gonna get to, you know, in a minute, because when you run the autocorrelation function, you're gonna see some kind of strong autocorrelation. Yeah, but yeah, we're gonna get to that. Yeah, in a minute.
Thank you.
Yeah. Okay. Oh, so right now it's 8:10. All right. So why don't we take a short break, 5 minutes break, and we will come back for more. All right. Welcome back. Okay, let me see. Yeah, Vivian say you just read the book Brand New World, so you are very pessimistic about the future, right? Yeah, then you are in this so-called, if you are somebody is very optimistic about long-term human, whatever civilization, and then right now people are starting. We might know whether there's aliens or not, right? So are you kind of feel like what's going on here? Yeah, so a lot of things going on. But anyway, if you are very pessimistic or you are optimistic, then that is deterministic view, trend view, and stochastic view is we don't know. We can go very well or we can go very bad, and human mind also might play a very important role in that. So that is more stochastic view. Yeah, Eric, you are saying something different.
I think I misspoke.
Yeah.
I meant to say stationary trends.
Yeah.
Or non-stationary.
That's right. Yeah. So basically, that's it. Yeah. But yeah, sometimes it's okay. A lot like this kind of package like AutoArima. Basically, I feel like they had this kind of default setting that just treat a lot of series like a non-stationary stochastic trend series. You might end up with a very similar result. Yeah. So, yeah. So, all right. So this is why I say real GDP like non-stationary, and when you kind of do this transformation, it become stationary series, and this usually is kind of easier to model, to forecast rather than that. But later I will gonna show you if we just kind of incorporate the ARIMA model directly, we're gonna see something also very interesting. All right. Okay. All right. So so right now I'm gonna talk about even kind of more interesting stuff. You might wonder why I had this picture. Yeah, I'm gonna explain later. All right, so kind of right now, let's use this ARIMA, these things to kind of explain all kinds of time series data. For example, you heard of this so-called white noise, right? It's like a random noise. So when you had that white noise, and if you run the ARIMA model, you're gonna get this so-called 000. It means what? There's no signal at all because everything from the beginning to the end is just pure noise. Right? So 000. Okay? All right. And white noise is what? Stationary. Yeah. And then we have this typical like auto regressive series. So that's the same thing you can find here. And if that is significant, you can take advantage of that to capture that and then predict some kind of a cyclical pattern. Moving average, similar things. All right. So random walk. When we talk about random walk, and here this is a pure random walk. So it look like this, 0, 1, 0. Okay. So just remember, random walk is different from white noise. White noise is 0, 0, 0. So it's flat. But random walk, it could have some kind of trend. But that trend is stochastic trend. So when you see the trend, also, remember when we talk about this profit function model? Remember that profit model we use, developed by Meta? That profit model basically cannot detect that is stochastic trend or deterministic trend. Usually they just view that anything they saw is a deterministic trend. And sometimes they just make a huge mistake. Yeah. So that is something I provide a warning before. Remember? Because I know profit model is not that sophisticated to kind of see some kind of historical trend as whether deterministic or stochastic. So usually they just default setting as a deterministic, and usually it could be very wrong. So pure random walk is here, 0, 1, 0. So nothing here, nothing here. So when you see something like this, basically you got this unpredictable result, right? And most of the random walk series actually is kind of combination. There's this part, which is unpredictable part, but there's also P and Q part, which is predictable. So you got this combination, right? Okay, so that's the random walk. And right now, I'm gonna talk about this even more interesting. So there's a thing called random walk with a drift. Have you heard of that term? Okay, later I'm gonna show you the even like a simulation. Okay, so random walk with a drift is we had this ARIMA part, 0, 1, 0 or P1, PQ, doesn't matter. But that's a drift turn. And this drift turn actually is a deterministic trend. So actually, this final one is so funny. It say some series when you see it, and there's a some trend. And actually, there are two trends in there. One is stochastic trend. One is deterministic trend. You have both. All right? And this is the part you can easily capture and predict. And this is the part you cannot. So you say, oh, this is kind of weird. What's that? In fact, I can tell you. Like S&P 500 series, like stock market, if we are looking at like long-term time series, it is like that. Stock market series is a combination of deterministic trend and stochastic trend. So let me give you some kind of rationale behind that. So why? Remember I said if anyone here is a finance major, in finance, all right. So deterministic trend, that means that there's something fundamental in there, and it could be related to say some kind of certain GDP growth, right? So when you had a GDP growth or whatever kind of similar kind of pattern of inflation, so that is supporting the stock price in the long term to follow that kind of constant growth. Because so you can say this is a fundamental part, and that fundamental part seems to be pretty stable over time. And at the same time, stock market has some kind of influence by a lot of news, like so stock market has been a little bit kind of volatile in recent days, right? Because of what happened in Middle East. So that is kind of very stochastic part. Something shock happened and it just kind of changed it, this stock price trajectory forever. So there's a combination of both. So, all right. So let's go back to that random walk down the street. People like drunk men as an example. All right. So I don't know if you had a dog or cat, and if you had dog, right? Being a responsible owner, you need to walk your dog every day, right? So let's just say you walk your dog to the nearby park every day. So, and when you walk your dog, your destination is a park nearby, right? So the process from your home to the park, that is what? That is deterministic trend, right? Because you're gonna end up at that destination park, and you're gonna come back. So that's the concept of deterministic trend. But every day you might go a little bit different path, right? Sometimes you go this street, and not sometimes you go different street, right? To change the scenery whatsoever. It's okay. You're gonna end up with that part as a destination. That's the deterministic trend part. Okay. So okay. So right now, and you leash your dog, right? And then so basically the dog can walk around you, right? So he cannot deviate from you too much because you are sober. You go to the park, so you're pretty sure the dog will will be in the park, right? So the dog will be there. All right. Let's just say you had this kind of very elastic leash, kind of the dog can go very far away. And then let's just say one day it happened, your dog just drinks some kind of alcohol on the ground. So your dog become very drunk dog. Yeah. All right. So rather than drunk man walking down the street, is right now the dog you walk become very drunk. All right. So you see this kind of two series getting together. The walker is very sober, going to the park as a destination. But the dog is totally drunk, so he doesn't know where he's walking, so he could go here and there. But because he's on this long leash, so even he's very drunk, he still got constrained by the walker because of the leash. So there's a kind of a relationship here. So the whole process, if we track the dog, walking process, will be this combination: random walk with drift. The drift turn is deterministic trend, is the walker's path. It kind of constrain that random walk to some degree. So that is something I'm gonna show you the real world example and some kind of simulation, so you will get to know more. All right. Any question about the concept here? Okay. If not, let's see some example. Okay, so let's load this a bunch of important economic financial series. S&P 500. This is oil price. This is exchange rate U.S. Europe. This is payroll. This is 10-year yield. Okay, CPI. This is auto. This is population, home price. All right, so we got that. Okay, this is two nice series. All right, nice series. All right, S&P 500. So when you look at this time series, all right, so how are you gonna model that and predict their future? So one easy way is this ARIMA model we just learned. All right, because it can just kind of auto ARIMA and help you. You're gonna see. All right. So before that, remember we talked about this uni-root concept, right? So this is uni-root test. There's a whole bunch of uni-root tests. So this is one, like a popular one. So let me quickly go over that. So, and there are two different kinds. Here I use this so-called KPSS, so sometimes the non-hypothesis of the test is kind of a little bit tricky, so make sure you understand that. So here, this is reject the none. All right, so maybe, okay, let's see what's going on here. I kind of forget what this is about. All right, so here, KPSS unit root test. So here, the test statistic is 25. And significant value is this 1 point, let's just say 0.4. So basically it's bigger than that. So this is like a right hand test statistic. Later I will tell you some kind of left hand, usually it's more common one. But anyway, so this is we reject the non-hypothesis. Did I say this is a hypothesis? Yeah. So reject the non-hypothesis. And the non-hypothesis is it doesn't have a unit root. It's stationary. Reject it, so it's non-stationary. It's having a unit root. All right. So S&P 500 has a very strong unit root. All right. Oil price, yeah, the same thing. Same thing. Yeah, unit root. Everything is unit root. However, let's see this one. So this is payroll. If we take the difference, did you see that? The test is 0.052, so it's less than all of this. So this is stationary because we cannot reject the non-hypothesis. All right, so this is kind of a unit root test, but sometimes, it's good do the test, but usually I don't. I just kind of like run this auto ARIMA. All right, so let's see. So S&P 500 stock price index. So did you see that? Did you see this? ARIMA 010. So what is that? So did you see this one? It means there's a stochastic trend. And in order to model it, you need to take the first difference, right? And then it becomes stationary. After it becomes stationary, there's MA order here. Although that MA order is relatively small, 0.08, all right? But anyway, you still can use it. Sometimes we call it momentum effect, so there's a momentum, so like, you just kind of, people just kind of buy, or sell, those kinds of momentum, right? So that's that stochastic part. Did you see the drift? Did you see drift here? So that is a deterministic trend part. So actually, stock price is a kind of perfect example of a series that's both stochastic trend part, not predictable, drift part, predictable. Yeah, but that is kind of long-term things. All right. So if you ask me, usually people ask me in the economic outlook conference, I would say, just based on this, it gives you a very strong evidence. If you ask me about personal finance suggestions, you just buy S&P 500 like VO, those kind of index fund ETF, and you keep it long term. You will be happy in the long term. Why? Because of this. There's a deterministic trend part. Pretty sure you're gonna get good. And I think if you ask Charlie Munger and Warren Buffett, they all agree with this. So this is the part. But if you try to make a profit in the medium term, so from next year to next year, that is a stochastic part. That I'm not sure. So yeah, so there's a difference. Whether your investment horizon is it is long term, very good. Medium term, this part not quite sure. And then you say, how about this one? This is kind of predictable, but that is more like a momentum. That's like a little high frequency. I heard that like a Wall Street firm, maybe some of you know that, this big trading desk, Wall Street, they had this huge supercomputer, right, doing this high frequency trading. They are trying to capture something like this short-term momentum. There's some kind of noise, and then noise deviate from fundamental. Then they do this kind of hedging things. So yeah, that is something probably you can also make some kind of profit of. But usually that is this is long term, pretty good, safe investment result you might be able to see in the long term. So yeah, to some degree, things like I'm a little bit deterministic, right? So in terms of investment, because if in 100, not 100, 100 years, probably we all die here, right? So probably, so I'm talking about like 50 years, like investment, whether it will be good or not. Things like, I'm a little bit deterministic, pretty optimistic in terms of a stock market, Okay, oil. Okay, oil, you see, is 212 with a drift. Actually, oil also had a drift. That's very interesting. But you know what? The drift, the coefficient is very small compared to stock market. So be careful. That doesn't mean a lot. So it's not that good. Exchange rate. Okay, so it's funny. Exchange rate is a perfect unit rule, 010. So basically, there's nothing. So usually in the economic outlook conference, people ask me about the dollar index. I cannot really tell. I know this because this is just kind of random walk, pure stochastic trend. So there's so many factors impacting the exchange rate. So it's extremely difficult to predict. Like sometimes I also do some kind of economic analysis on Chinese economy, and the Chinese currency is just so weird. So sometimes you thought it's gonna depreciate a lot because their economy is not doing well, and in recent months, all of a sudden they are appreciating. You know, so it's kind of weird things going on. Yeah. Anyway, yeah. Payroll 0120 with Drip. Treasury yield. Okay, I don't know why it takes so long. Then you know, right, 214. That's pretty complicated stuff with Drift. Yeah, all right. CPI 023. So CPI means what? It take the difference twice. So when CPI take a difference, it become like a definition like inflation rate. But even inflation rate is pretty stochastic. So we need to do another round of difference. So that is why this is 2. Yeah. Auto, okay. This is the series you guys are doing for your assignment 4, right? Did you find it interesting? The practice interesting? The assignment 4, right? Building the model from scratch. You know, that is how you right now through that assignment 4, you learn how to kind of really build a model, you know, based on all kinds of information you could have with some kind of instinct, with some kind of model. All right, population, now 021. All right, home price 1, 2, 3. All right, so right now, let's look at this auto REMA. Let's kind of make a forecast and then see what's going on here. So this is I believe S&P 500. All right, so this I think this is weekend, so no series. So based on this, you can say, all right, it's upward, right? But with wide range. So this upward part is that deterministic trend part, that coefficient it capture, okay? So for whatever reason, GDP growth, population growth, you know, profit growth, you know, AI whatsoever, you know, inflation, the stock price is going up, yeah. And then with some kind of uncertainty, yeah. So that's that. Okay, oil price. Okay, oil price, did you see a little bit down here? So that is kind of that short-term whatever ARMA things. And then after that, it become pretty flat. So you're gonna see something like this, exchange rate. Okay, so exchange rate. Did you see what is the prediction? It's a flat. Okay, so let me tell you a term. It's a very, very fancy term in predicting, in forecasting, called random walk forecast. Have you heard of the term? Anyone here? Random walk forecast. Sounds like a very sophisticated term, right? In fact, you are looking at a random walk forecast. And what is a random walk forecast? Random walk forecast is because we detect there's no signal at all. And the series is pure random walk. So we cannot really predict it. So what we are doing is that we use the final observations value as a prediction forever. Right? So basically it's pretty dumb forecast, right? Whatever the final value of it, we just use it forever. So that is the random walk forecast. Yeah, that is. Yeah, so basically, yeah, sounds very sophisticated, but actually it's that. And you say, why? Why you are predicting? Because stochastic, pure stochastic. So the best way is this. So don't laugh. Actually, I'm using something like this. For example, in some kind of project I'm working on, stock market performance is one of the input. All right. So I have this structural model, and one of it is stock market performance. And remember, I said you run the model. If it's a structural model, you need to forecast all your inputs future first, right? In order to forecast the dependent variables future. So every time I put the stock market components forecast, I always use the final value of the stock market as a prediction. So actually, I'm practice what I preach. So it's a random walk forecast. That is my forecast. All right. So let's yeah. So yeah. And in your assignment 4, if you pay attention to, sometimes you got something similar to that. ARMA model maybe they doesn't have a lot of change too. All right. Anyway, so payroll. Okay, so this is kind of rising. Oh, pretty good. So our ARMA model telling payroll, labor market will continue to grow. Very good. What's this? 10-year treasury yield. What's it? Is it? Yeah, 10-year is almost like a random walk, pure. So CPI. Oh, CPI. Okay, price will continue to rise. Sorry to know that. Yeah, auto. Okay, so this is something you guys have predict, right? So it's pretty flat. So up to some point, it's kind of flat. Population, okay, good. All right, home price, oh, pretty good. So if you're a homeowner, you feel very good. As a whole, home price will go. If you are not homeowner, you want to buy, you say, oh, that's not good. It's kind of getting more and more expensive. Okay, all right. So and then we have some kind of comparison here. So you guys can kind of look at this on your own. This is more minor detail. Okay. Yeah, this is drift turn. Cross validation. Yeah, okay. We don't have the time. You can kind of practice on this, on your own. So this is kind of like what I'm talking about. The random walk with a drift turn, and that drift turn turned out to be pretty good, in terms of understanding the long-term investment return. So this is something like this is saying that CAGR is 4.5%, 7.5%, and basically, it's coming from that. Yeah, you can kind of just look around on your own for that. Yeah. Okay. Should I talk about this? All right. So let me see if I can. Let's see if this data is still available. Okay, all right. So let's take a look. Okay. So this is COVID data. Actually, COVID, ARIMA model can apply in any kind of time series. So this is COVID. I think it's accumulated deaths data, right? So this is daily data, and this is, I believe, is New York City. We have this data. All right. So right now, so this is probably 800. So this is whole like the first 2 years of the data set. All right. So right now, let's model it. ARIMA, and we got it. Oh, this COVID accumulated deaths is 223. And so actually some institutions use this ARIMA model to forecast these kind of things. All right, forecast. So basically, this is the forecast result because it kind of dictates this pretty flat, so it continue to predict the flat. And it's not wrong. It's pretty accurate. So because basically, the situation just stabilized. All right. So this is Los Angeles. Let's take a look at Los Angeles. Also, kind of similar. Right. Okay. So this is kind of like a all right. So we got pretty good result, right? But I just want to tell you, you need to be careful about using this ARIMA. So it's pretty good at short-term forecast, but sometimes it's not good at long-term forecast. So let me show you what's going on here. So if we just use the first 70 days as the trend set for this COVID death data in New York City, all right? So here I just choose the first 70 days. And then we can check the testing set, right? Because we know the rest. And then we forecast. Okay, let's see what's going on here. Okay. So this is the actual COVID death, right? We just saw in the first 800 days. And here, this is what we have. We use the first 70 days COVID deaths as a trend set, and we make a prediction. So ARIMA, right? So we figure out the ARIMA, and this is what we predict. So do you think it's a good prediction? Of course not. Just kind of predict this, and then yeah. Although it recognizes there's a huge wide range, right? Okay, that is correct, you know, but yeah, sometimes you still need to provide some kind of point forecast, right? So it's totally off, right? So that part is not correct. So I just want to tell you, this kind of ARIMA model is not designed for long-term trend. So long-term trend model, it could kind of be misleading. Even it had a way to determine the deterministic trend, stochastic trend, but we need to be careful about using it. And something like this is the reason I intentionally use the first 70 days is because I know in retrospect there's a turnaround, huge turnaround point. And ARIMA model cannot capture that, right? Typical, because later I will explain more. So something like this is not that easy to predict. All right, so let me show you another one. So let's trend for Los Angeles data set for the first 250 days. You say, first 70 days is too short. All right, how about first 250 days for Los Angeles? Yeah, right? So we used it here, and it predicts this. And the actual one actually is much higher. So again, this is not a good model. It cannot give you the very accurate. So kind of come back to what we had talked about before. Forecasting the future is not that easy. And why? Because like model like ARIMA model, this kind of thing, under the kind of very fundamental assumption, the signal is fixed. But here the signal change. For whatever reason, we got a second wave of COVID in Los Angeles. So this doesn't hold, all right? So yeah, ARIMA model cannot predict the turning point structural change. So later I will explain then how are we gonna improve it, fix it. I will tell you about it. All right, any question? Okay, all right, so right now let's look at this H05B simulation. All right. So we talk about this random walk, right? So here, let me show you how to simulate this random walk or even with strip term. All right, so this is a function. All right, so we have 4 inputs, number of the series, steps, and x0 is a initial point. Usually simulation, you need to decide the starting point, all right? So there's a mu, and what's mu? So it's here. So this is a deterministic part. Did you see T? T is from 1 through n. So this T is like a capture that kind of time trend. Remember the time trend model we are talking about? So here, that is that time trend series 1, 2, 3, 4, 5. And the mu is that coefficient of the time trend. So that is the coefficient of the deterministic trend. It's like the trend model 1, 2, 3 we learn, right? We can kind of estimate that. So that is this. Okay. And Z, this is part. Did you see that? I don't know, Python had exactly the same kind of way. Constant, are you guys familiar with this constant? Constant actually is a very good function you should know. All right, constant is like a accumulation. So you have some kind of series and you just add up the previous value as it, adding the sense. It's a constant is very kind of check it out, kind of check GDP, Google it whatsoever, right? Constant is a very good understand. So what happened here is this simulation is a typical one you guys are very familiar with. This is like a normal distribution random generation, right? RNOM. So we generate mean is 0, standard deviation, whatever you want to set it on, right? So this is like a random noise. This part, random noise. You're gonna say some kind of normal distribution random noise. However, when you have this constant, it becomes a random walk. So that means what? Use random noise, the sensing generate here, the value you generate here even is a noise number, but is the next number is gonna based on the previous number. So it's contingent on the previous number. So that is accumulation things. All right. So maybe right now it's too abstract, but later I will show you. You will understand what I mean. So this is a pure random number, and with this constant, it becomes a random walk. Okay. Random walk means what? Although it's a random series, but it's contingent on the previous series. Okay. So that is some kind of contingency. All right. So for example, we say the random drunk man walking down the street, right? So you don't know eventually where he will end up. Maybe in the ditch, maybe at home, maybe in the police department, right? But we know for sure he cannot fly, 2 blocks away, next step, you cannot fly because he need to walk one step by step, even if he's very drunk. Yeah, so let's, all right. So we had that random walk, and then this is the deterministic trend, this is stochastic trend, and this is just beginning things. All right, so let's kind of run that. This is function. Okay, so let's see. So here we simulate this 120 step, and initial value is 10, and this one mu is 0. So means what? Let's know deterministic trend, just random walk without drift, and variance is 0.001. All right, so let's run that. Okay, run this, and plot. Okay, so this is the first random walk, beginning from 10, end up with 10.4. All right. Second one, you see? Did you see that? We starting from the same point. So basically, P1, P2 is the same coefficient, the same place, but end up in a very different place. This is the idea of random walk. You drunk man walking down, you go out here and then eventually go out here because what? It's in there random walk. And even let's things like there's a trend, but it's pure stochastic. All right, so let's see. Yeah, P3 random walk, and not in a different place. P4. Okay, so the same starting point and not totally different destination. Random walk, stochastic trend. All right. So right now, let's kind of add this drift term. So we have some kind of deterministic part of it. So let's see how it goes. Fine. Okay, so random walk with a drift. Okay, so let's try another one. Okay, did you see that? It ended up in a very similar destination. Let's try another one. So this is very interesting, right? So although in all the middle part, they go far away, that is stochastic part. But eventually, it seems like they all end up in a very similar place. All right. All right, and let's try this one. So this coefficient is even stronger. Let's see what's going on here. Yeah. So it's both. So there's a lot of uncertainty here and there. but it seems like they end up in a very similar place. Okay. All right, and this is some kind of simulation about, let me see, yeah, this ARMA. So just kind of in case you are very curious, what's going on here. So let me show you. This is AR1, and when the AR coefficient is 0.7, so it look like this, and yeah, okay, yeah, this is autocorrelation function. You can take a look on your own, All right, and this is with a random walk simulation here. Okay. Yeah. So basically, yeah, let's say, yeah, you can play around with this. Okay. All right, so let's look at this. So kind of revisit. Oh, Vivian, you had a question?
Yep, quick question. So, kind of basic question, but when you're deciding to try like all of these different functions, like is there a process that you like that we should know about in order to like test things systematically? Like, P31, P30, like, and deciding like how to change the variables. I mean, like, yeah, like, is there a method
Oh,
to doing it in a very organized way? Like, do you have some best practices?
no. This is the no. This one, for example, I show you this like a ARIMA model, right? Where is it? Yeah, here. This is basically, yeah, this is some kind of criteria eventually can help you determine what is the best model to capture, to mimic this time series. All right. So there's a way, like usually I will look at root mean square error whatsoever, right? But this one, no, this is just pure simulation. This is kind of like you want to understand more about this kind of underlying dynamics. So you play around with settings. So basically, this is like a parameter you want to be sure. So this is pure signal and incorporate some kind of noises. So it's kind of is reverse engineering. Usually when we do the data analysis, we look at the data, we try to figure out the signal. But this one is like, all right, so let's reverse it. You set out a signal, and let's see how it plays out. Like in the real world data, how it will look like. So it's a little bit. You can play around this all whatever you want. It's just simulation.
Okay.
Yeah, it's different. All right. So you can basically it's like this is for your own kind of understanding and practice. Yeah, there's no rule. You can do whatever you want. Yeah.
Okay.
Yeah, we're gonna talk about more some kind of simulation. Sometimes in nowadays, even like in AI, they are talking about like all right, we already trained all the AI model with all the data available, right? So right now they are talking about this kind of synthetic data. Have you heard of that? Like they are generating the data and then use that kind of generated data to train their cell. That's more like this kind of thing, simulation the data and then use that. We're going to talk about something more like bootstrapping things later on. Yeah. Okay. All right. Okay. So here, deterministic trend linear. This is something we've seen before, right? So basically, GDP, right? All right. So this using these functions, this trend. So basically, we assume there's a deterministic trend, linear trend, and then we model it, we forecast it. Something is wrong. What's going on here? What's going on here? Anyway, yeah, you guys can check it out. So it's kind of forecast and then it will look a little bit different. All right, so this one. So this is something I'm gonna talk about deterministic trend. Yeah, okay. I'm gonna come back here later. So let's go to the lecture notes. Where's my slide? Yeah, my computer is a little bit funny. I don't know why. Just give me a second to open that. Okay. All right. So right now, we finished this ARMA model. Let's kind of expand it to this dynamic regression model, even more general kind of form. So let's look at some kind of interesting things first. All right. So here, so this is payroll job number percentage change since 1990 in various county in California, right? So, so this is Riverside because it's inland. You know, for those of you who are not familiar with, it's kind of like a cheaper land, so it kind of grow faster. Yeah, inland. We call it Inland Empire, Riverside, San Bernardino, and we have various like San Diego, Orange County, Santa Clara, Oakland, Los Angeles. All right. And sometimes some county had higher growth, job growth, sometimes had low one. Los Angeles had low one. Yeah. But did you guys notice there's one county had a little bit different dynamics, right? Anyone know? Notice that? Right. Santa Clara, which is Silicon Valley. So it seems like it has different kind of dynamic, right? So when I first see this, I said, "Oh, this is interesting," you know, because other county, they seems like they follow some kind of typical business cycle, right? When the economy is growing, it growing up, all right, and then this, and they go down. This Great Recession go down, right? So it seems similar, but you know, sometimes it's just some is higher, some is lower. But Silicon Valley seems like it had a little bit different dynamic, right? It grow faster, it decline deeper, you know. Anyone know why? Because this is dot-com bubble. Yeah, dot-com bubble bust. Yeah, all right. So they had this kind of additional interesting dynamic, all right. So this is actually a presentation I did to the Santa Clara County. So I put this together. So this is a Silicon Valley job, and this is NASDAQ index. NASDAQ index basically had a lot of big tech, small tech company, yeah, over there, right? So and in this different right and left scale. So did you see a pretty, you know, similar kind of pattern, right? All right. So can anyone tell me, just by this visualization, is anything else you observe which is very interesting? Some kind of interesting dynamics in addition to that kind of flow, very similar pattern. Anyone notice?
NASDAQ is leading the payroll employment.
Very good. Exactly. So there's one thing very important. Did you see the peak here? Right. It peaked around 2000, the earlier 2000, and the payroll job actually peaked almost 1 year later, and dropped. It bottomed out in the middle of 2002, and the payroll job bottomed out a year also late. And this kind of pattern should continue. It peak and the payroll peak. Stock market bottom out. So usually we say stock market like this is very good. Nasdaq is a very good leading indicator for Silicon Valley's job labor market. Okay. So when you observe this pattern, will you be able to explain this pattern? Does that make sense? Anyone? Try to explain this. So
sorry,
yeah.
go ahead.
No, you go ahead. Let me see your explanation. You observe this pattern, seems like it's pretty persistent. There's a lead-lag relationship between stock market and job market. So how are you going to explain that?
So it's like if the companies are doing better, their stock market grow, their stocks grow, they make more revenue, then they hire more people. When the companies do bad, the payroll employment drops down because they let go of more staff.
Exactly, right. So and it takes time for human resources department to hire people, doing the interview and then take a time. So yeah, it kind of makes sense, right? It takes some time to this new hire to come to the company, and layoff also take time. So yeah, so let kind of explain this, you know. So yeah, it should not be surprising to see that. All right, so right now. So this is actually a real case. So when I observe that, you know, how can I model it? You know, I need to have a kind of pretty serious way to model that to make sure I have that. So actually, this is what I do. So here, YT is, I think it's monthly data or quarterly data of Santa Clara County job. And XT minus 1, you know, because I observe that lead-lag relationship, so it's kind of lagging. And this is Nasdaq index, all right? However, I think this is not enough. I do this. Anyone know why? The data here. So this kind of come back to what we have been talking about. Because YT, XT, this is, you can say it's very non-stationary, right? And this kind of trend, you know, sometimes, remember in the very beginning, I talked about this so-called spurious correlation. Anyone remember the term spurious correlation? So I actually emphasize, if you put any kind of a two series with no relationship at all, but both has some kind of trend, and if you run the correlation, run the regression, you're gonna get significant correlation. That is spurious correlation. So we need to be very careful, and the reason is because both have trend. And so that's why I emphasize in these 2 weeks is when you analyze data, especially time series data, be careful. Make sure it's stationary, because if it's not stationary, usually has a trend. And you put these two series with two non-stationary series together, you're gonna get spurious correlation very easily. And that is not good, because you know you don't want to fool yourself. So here, the things I observe, although I can tell a good story, but it could be some kind of spurious correlation, right? So I want to avoid that. So not only I run this, I also run this. I kind of take a difference, and then and turn out to be both had a significant correlation. So I am kind of more confident. So this one, because when you do this difference or growth rate, the series, the regression, the series becomes stationary series. So by doing this kind of transforming to a stationary series, you avoid the chance of spurious correlation, and then that is very important. All right. So that's why in assignment 4, did you follow my guideline? I say run, check, make sure the regression you run is a stationary series. That is because of that. Because if not, you kind of run any kind of two series, with a trend non-stationary, you're gonna get a strong correlation, and then that is not a true underlying signal. Yeah. Okay. So all right. So seems like we are running out of time. So I'm gonna stop here, and I'm gonna continue to talk about this and finish that, and yeah. But anyway, I think you can work on assignment 5. Just follow my guidance, and then submit in by time. So next week we still have lecture, right? The week after next is a spring break. So we are gonna talk about complete this and talk about something more next week. All right, so that would be all for today. You guys have a good night, good week. I will see you next week. Bye bye.
Thank you.
Thank you.